Pest Management by Chris Guiver.
Thanks very much. Okay, good afternoon. Thank you very much to the organisers, to Paul and Andrea, for inviting me and enabling me to come to Brazil. I've never been before. It's a beautiful country and I'm really enjoying Rio, so thank you very much for the invitation. So I'm here with a contingent of people from the University of Bath, and I'm interested in mathematical control theory. Now I expect, or I guess, that this is not the area of expertise of this audience, and so although there are lots of words in this title that perhaps you know what they mean sort of in English, well, maybe not technically. So this talk is reasonably elementary and it describes some sort of recent work that I've been doing with many others. So I shall present, the colours are just to help vary the text a bit. I shall present some work on simple adaptive control. I'll tell you what I mean by that. And this is a class of positive state systems. And more generally, I am interested as a sort of mathematician, or as an applied mathematician, in this idea of positive state systems. So broadly, these are dynamical systems where the state variables must take non-negative values because they correspond to non-negative quantities. So you can think of a number of people in this room. It's what, about 10, 20 or so? We can't take away more than 20 people. It's not meaningful to talk about the room having a negative number of people. I'm completely happy with negative numbers. I'm not disputing they exist. But in some contexts, particularly modeling, non-negative quantities are meaningful or important. And that affects how we can control them. Okay. So this is joint work. It's nice to show a slide full of smiling faces. This is a potential application, I should say, is in pest management. I'll get to that. So it's been born out of collaboration with Hartmut in the top left. He's at Bath. The next two are in Exeter, Stuart and Marcus. And then a tranche of Americans. So this is Richard and Jim, Christina, Brigitte, and then Eugene, collaborators in America. So just to sort of give a schematic of my overview, these are areas of mathematical, applied mathematics which are represented at Bath. So I come from a background in systems and control theory, and again, I'll try and explain what I mean by that. And broadly, lots of problems in mathematical biology can be addressed or posed in a systems and control framework. So for example, we study SIR models to know primarily how you might control a disease. But then that gives me the sort of top arrow. Of course, then problems arising in mathematical biology require new tools, require new mathematics, which forms then the bottom one. So these are two research groups, if you like, at Bath, and I sort of sit between them. So I keep talking about systems and control. I'll spend a couple of slides trying to explain that. It's hard to describe systems theory without making it sound really boring, but I assure you I don't think it's boring. I think it's very interesting. Broadly, I would say it's the mathematical framework for interconnecting dynamical objects. It probably arose out of sort of circuit theory in the 1920s. So an electrical circuit is made up of transistors, inductors, capacitors, resistors. And if you put these together in various configurations, you get a sort of electric profile, which was then inform, okay, maybe not an analog watch, but all electrical devices. And that is organizing dynamical objects. So then control theory, also sometimes called control engineering, is quite a broad discipline. On the one hand, it is people who build things through to people who design and analyze them. And it's trying to design a dynamical system so that when connected, we get some desired dynamical behavior. And I'll illustrate that sort of through examples. And combined, it's a language for describing feedback. And feedback was mentioned in just the second talk of this workshop. Feedback is everywhere. So central heating systems, a good example of feedback systems. Your body has homeostasis, is the process by which the body regulates itself. So you stay at right temperature, you shiver when you're cold. Your blood hopefully contains the right amount of insulin, which is sort of, when that goes wrong, we have diabetes. So systems and control helps us mathematically write down feedback. So these sorts of diagrams are often used. The plant comes from sort of engineering a chemical plant or a power plant. Think of like a big, big building. Some measurements are taken from part of that plant. They're then fed into a controller, which might be just a black box. It might be in silico. It might be a computer model. That then gives you some instruction for how to then control your plant. Part of systems and control is predicated on understanding uncertainty. So these systems might be quite noisy or poorly understood. So I've redrawn the picture. I'll make it a little bit more mathematical. Optimal control is a part of systems and control theory. And this means choose C. P is often given. It's the problem you have to work with. choose C so that when I combine these objects, not only do I get some desired behavior, but also I minimize some functional. I do it optimally. I do it in the least amount of time, or I spend the least amount of money, or the least amount of energy, say. At the other end of a spectrum, and possibly lesser known, is something called robust control. And this takes the idea that P actually belongs to some class or set of models. And you might know the set of models or know something about them without knowing the exact model. Okay? And so, roughly speaking, your C is robust if it works, whatever works means, for every P in pi. And the bigger pi is, the more robust it is. And what's difficult is that optimal and robust control are at different ends of a spectrum. Controls that are robust are not often optimal, and vice versa. We can illustrate this with an example. At some point, I'm going to fly home, and you'll get on a flight at some point. If we say that waiting at an airport is boring, a natural question is, well, when do I leave to get to the airport so that I spend as little time there as possible? Now, of course, you could say, well, work back. How long does it take to get to the airport? Let's say an hour. I leave an hour before I need to get to the airport. But of course, then if you have some uncertainty, if you get stuck in traffic or if you break down, you might miss your flight. And that would be very bad. You've not optimized your problem at all. You have to wait for the next flight. If, in fact, you left 2 hours, then you have got some robustness with respect to delays in traffic, with respect to delays in, you get a flat tire or something. But then you have to wait longer at the airport. And so often, what is robust is not optimal, and vice versa. So, moral of the story is that a lot of work has been done on optimal control of pest management. And we're going to present something from robust control. Ideally, you meet in the middle. You have something that's not optimal, it's suboptimal, but at least it has some robustness. Whoops, sorry. And so, in case you've never thought about this, trying to control something you don't know faces challenges. It's difficult, right? Because you cannot use your model to build your controller because you don't know your model. But I'll explain this with more mathematics. Okay, so I'm going to focus on something called stabilization, which means you have an equilibrium of P that's unstable. Choose C to make it stable. Make something, an unstable equilibrium, stable. And we're going to say that P is going to be linear, positive, and it's not likely to be well known, so we want a robust control. So construct a suitable C and prove that when I combine them, I get desired properties. Okay, so that's a little bit of background. The motivating example, time for another picture, comes from our ecologists in the US who are concerned about this weevil. I won't try and pronounce the Latin. This weevil is native to the Caribbean islands, and by accidental transport, it was brought to the United States in the 1960s. And it is a citrus pest. It eats lemon and lime and orange and things. And so this is an economically important pest in southeast United States. So natural question is, I'd like to control it. I would like to sort of deal with this pest. This is part of the, I'm putting my cell hat on, this is part of the food security challenge of the 21st century. And just to illustrate how hard it might be to control this, I'm going to explain the life cycle. Now, I'm not a biologist. This is given to me. So females deposit eggs on leaves of plant, actually on the undersides of leaves. These eggs hatch into larvae. They drop to the ground. They burrow underground. So already they're underground. You can't see them. So it's very hard to count them. It's very expensive. And already they start to eat the plant. So what you might ask yourself is, if I have a pest infestation, well, how do I know? I mean, you could use your reduction in yield as a proxy. I'm not generating as much crop, so I must have a pest. But if you actually want to count the pest, well, it's very difficult. So generally what happens is you sample some of the adults, and I'd argue it's challenging to study if you have DRW or not. And bear in mind, the people who have the pest, the farmers, US farmers, they're armed, and they're quite sort of set in their ways, apparently. So there are challenges practically implementing this. This word means, has distinct life cycle stages. Endorogopty, insect, can be killed by chemical pesticide. Of course, chemical pesticide has environmental considerations. An alternative is so-called biocontrol. So this is a pest pathogen, something that eats pest. So nematodes, which are like small worms, can be used to eat a pest. So there are alternatives to chemical pesticide. So, I mean, as mathematicians and sort of statisticians, I'm sure you can appreciate this picture. It's more for biology. I have this framework, PC. I'd like to fit this to my model. So that I would have my pest model. I sample the pest, I give a recipe for designing a control, and then I feed that back in. Of course, realistically, even if there is a model for pests, I'm not likely to know it. So there's a lot of uncertainty there. There's bound to be sampling error when I use my pest sentence to inform the management strategy. And then it's not necessarily a closed system. Things could leave and enter, which you're unlikely to know about. Okay. So I've hopefully said a little bit about systems and control. I've tried to motivate a real-world problem, which is pest management, which is why we're interested in this. I'm now going to go more into the mathematics. Stabilization by feedback. So it's very basic. Suppose this is a linear system, so x dot equals ax. So this is all going to be deterministic, and I'm going to jump between discrete and continuous time, because I'm mostly working continuous time, but sometimes it's done in discrete time. So linear model, x dot equals ax, some control action u. A and B are appropriately sized matrices. So a static state feedback means you take some proportion of the state, x, multiply it, or you take x, multiply it by k, and feed that back in. So you use where you are to inform your control. So if you can see, if you plug in 2 into 1, you get a minus bk, so you get a new linear system. This is 0 is an equilibrium if you have no u, 0 is an equilibrium, and it's stable if the eigenvalues of a minus bk are in the left half complex plane. That's what I mean by this symbol. So I want to choose k so that a minus bk have some nice properties. And then this has been known for a long time. If a and b have certain algebraic properties, you can always choose a k. However, and it's never unique, but knowledge of k depends on ab, right? That seems natural, right? In choosing k such that a minus bk has certain spectrum requires knowledge of ab. Well, what happens if you don't know a and b well? So using the stability radius, which is a concept from the 1980s, more or less by continuity, if you know k works for a given a naught b naught, then in fact it works, so stabilizes all ab close to a naught b naught. So this is a local robustness idea. I need a reliable estimate, and then I can stabilize in the neighborhood of that estimate. But suppose I don't know a or b well at all. There's a lot of uncertainty surrounding them. So let's consider a scalar example. I mean, the answer is I need a more sophisticated controller. So now I'm considering the same model, but everything's scalar. This is illustrative. Suppose all I know is that a and b are positive. So taking my state feedback, plugging it into 3, I'm going to get a minus bk. I want that to be negative. So rearranging, that means k must be big. That's the idea. Big K is good. But of course, how big? I don't know A over B. Well, what I'm going to do is I'm going to give some adaptation. I'm going to give some dynamics for K, right? So I'm going to replace it by a dynamic variable, K dot equals x squared. So notice the derivative is non-negative, so it's getting bigger. So the natural concern is, well, it might blow up, right? It could be unbounded. But I claim that this combination of 3, 4 gives x going to 0 and k remains finite. And this is a nice sort of algebra or a calculus exercise. If you differentiate this quantity at 0, so this quantity must be constant. This quantity describes an ellipse in xk phase space. So I've drawn circles, but I may as well have drawn ellipses. So some given x naught k naught, x goes down, k goes up. I hit this k-axis where x is 0. So this is what I mean by adaptive feedback control. You allow your feedback parameter to vary with time according to some update law, the present state or output. In sort of early engineering literature, this was also called self-tuning. And the point is, it's not, no estimate of A and B were required. It's not a local robustness technique. It's a global one. All that I know is that I need some structural properties. In particular, I needed A and B positive. If B were negative, this thing wouldn't have worked. It would have sent x down to minus infinity. So I still need some knowledge, but I just need a sort of structural property. And the word simple comes in because I'm not trying to learn about my model. Yes, that's an important observation. This is not really learning control, or in control language you'd call it systems identification. I'm not trying to learn my model. That's a viable approach. You could say just spend some more money, or do better modeling and learn your model, and then develop a controller based on that. That's just a different approach. Okay, so I'm actually going to skip that. All I should just say is that there is obviously a body of theory about simple adaptive control, but it's not based on positivity. That's a new constraint. So we're now going to be in the context of pest management. We're going to assume a very simple model, linear, discrete time, some control action. Y is a functional of the state, if you like. It's some combination of the state vectors, or some combination of the state components, which actually is highly idealized based on what I've said. So in our Weevil example, it might just be the adults. Now, this is a massive assumption, I agree, and I'll say a bit more about it later. So A in ecological modeling is called a projection matrix. This is a structured population model, so stage classes correspond to different developmental stages. T is a fixed time step, so it's weeks for DRW. V is a degree of freedom. I can choose that to achieve some desired dynamic behavior, and I'm going to try and use adaptive feedback control. But this represents a non-negative set of quantities. So a negative state would be meaningless. It's just not, your model is breaking down at that point. So this is a screen capture from the Max Planck Institute's website. It's a number of years old now. I should check it's still there. It's very easy, myself included, to be quite sort of haughty about matrix models. But the point is there are a lot of them. Ecologists have spent a lot of time and money finding these models, parameterizing them from real data. So they're readily available, and it seems a shame not to make use of them. So the first part's now modeling. If V denotes pesticide application, what form must it take? So it only affects life stages. So it might only affect the egg class or the larvae class. It must be proportional to how many are there. So again, if there's a call for lunch, say, and maybe only, sorry, start again. The people who can leave this room must be a proportion of the people who are in this room, let's put it that way. And in fact, it's probably some increasing function of some applied control effort. So suppose someone cries lunch from outside. The louder they cry, the more people might leave, but as a function of how loudly they shout. Maybe that analogy is a bit tenuous. But. So in particular, I'm trying to motivate that there's a nonlinear feedback, structured by B and F with some efficacy function. So that's what I've said. B determines structure in proportion to F, and phi represents some efficacy or lethality. How effective is your pest management strategy? So again, with our robust control hats on, we're not likely to know this function. How lethal a pesticide is not likely to be well known. In fact, all we're likely to know is that it's going to be 0 at 0. If you do nothing, there'll be no effect. It's reasonable to assume it's continuous and increasing, and in this context, it maps to 0, 1. So for that way, it's for U. And now, we still have to determine U. How are we going to increase U? So we propose an adaptation law, which is a bit like U dot was, ut plus 1 minus ut is a bit like the derivative in discrete time, yes? So U gets bigger in proportion to what we measure, i.e. what we observe from the system. So I've plugged my V back in, and then U is updated. So it's a dynamic variable. This is just the one norm. So psi is some sort of rate of increase. If we observe pest, we increase what we're doing, and how much we increase it by is determined by psi. So I'm going to assume that at some U star, this thing is stable, right? Just a spectral radius less than 1. And I'm going to assume that it's always non-negative and irreducible. These are sort of reasonable assumptions, and I've captured those as D. Okay. So here's the theorem. Suppose that my triple A be F and phi satisfy D, phi also satisfies F, and what I observe is something. That's a vector, remember, so this is understood component-wise. Then for any initial conditions, apart from 0, if you start at 0, you stay at 0, so it's not interesting. And I need psi to satisfy, this is a geometric series. Geometric series are finite, so psi needs to respect geometric series. So if psi is Lipschitz continuous, you're fine, right? It can be even Holder continuous, and you're fine. So in particular, x then converges to 0, and U converges to something finite. The algorithm or the strategy we proposed, x goes to 0, U goes to something finite. In fact, what it goes to must be stabilizing. So we published this in SciAm, Applied Maths, last year. Okay, so wherever you start, x converges to 0. And crucially, the proof is based on comparison arguments, and that irreducibility assumption is really critical. What that means is you can't have separate sets of dynamics. It could be the case that one part of the population is doing this, another part's doing that. You don't measure this part. You only measure this part, and you only control this part. And were that to be the case, well, you've got no say over here. So the irreducibility assumption sort of says, I mean, the life cycle graph must be strongly connected in graph theoretic terms. So without these assumptions, it won't work. And you could say, well, Chris, there's all this work on adaptive control from the sort of 70s and 80s and onwards. They come with certain structural assumptions, which I've not mentioned. They're not required here. And I won't comment on that. So in particular, to implement this, you do not need to know A, B, C, F, X naught, or phi. It's hugely robust to sources of uncertainty here. You don't need to know them. Moreover, unlike an optimization scheme, I mean, if you know optimization, sort of calculus of variations or maximum principles, they're hard, very difficult to actually compute. You could compute this with a calculator, or at least with a computer. So it's very easy to implement, at least theoretically. Okay. And I say it's a global robustness result because it's not based on a parameter estimate. So here's a simulation. Without any context, this probably doesn't mean a huge amount. So this is X. Over time, it goes down. U, the control, increases. I mean, this is a sort of dimensionless quantity. I've chosen different rates of increase. So this function is bounded. This one obviously grows very slowly. This grows much faster. This one's more interesting. This is phi of U. So it hits 1, which is as efficacious as it can be, and the dashed line is the spectral radius of A minus BF. So this thing actually limits at about 0.95, so that's the fastest it can decay. So over time, it hits that, and then X starts to decrease. What this simulation doesn't show is I picked one model. I randomly now generated 30 models and did the same thing. And although I can't predict the individual lines, I qualitatively get the same behavior. So that's why it's robust in that sense. Okay. So just pause, summarize. I've presented a simple adaptive controller for linear positive systems. There are many ways you could extend this or many things to consider. The one is the underlying model, right? Finite dimensional, linear, very simple. You could extend that. The other is the controller. What are you trying to achieve? And then less relevant for this talk, but there are connections to classical adaptive control. We're not completely reinventing the wheel, so we're sort of mindful of those. So I'm briefly going to mention how both of these can be extended. We've started this. The idea more or less remains the same, but the technicalities can be increased. So there's nothing particularly inherently finite dimensional. Well, there's one step. So A matrix could be replaced by an operator on a Banach space with a partial order. That allows you can treat integral projection models where your state space is no longer Rn plus, but a space of integral functions for some non-negative kernel. So whereas I had previously discrete stage structures, now I have a continuum. So typically this might be a tree diameter in millimeters. That's a continuous variable between 10 millimeters and 30 millimeters, say. So notice this isn't a spatial component, it's just a continuum of stage classes. And more abstractly, the reason why this is true is this inequality is crucial. When two operators are ordered and not equal, when are their spectral radii strictly monotone? And this depends on what you are prepared to assume about your operator and your space. So in the usual matrix case, irreducibility of A2 is sufficient for 8. By considering upper triangular matrices, if A1 and A2 could have the same diagonal, in an upper triangular that would determine the spectral radius, but they could not be equal. So this inequality is not trivial, or this implication is not always satisfied. So if you can find a class of operators where it holds, which it does for the IPM case, then you're in business. You can also work in continuous time, and now you need that the spectral abscissa behaves monotonically. So previously I had the spectral radius, now I have a spectral abscissa. So you could work probably in continuous time, infinite dimensions, if in fact you had some sort of inequality about the growth bounds of the semigroups associated with A2 and A1. So I just mentioned that. An obvious extension would be to models with a spatial component. This is particularly important in ecology. This is a screen capture from a paper that talks about invasive weevil, more or less you can see there are more dots over time. These things have a spatial extent and spread, and they're often modeled by integral difference equations. And of course, now there is really a big difference about where you control, because controlling everywhere means it's sort of global control. That wouldn't be practical or feasible. You'd probably control at various places in space, and how you choose those is a sort of big problem. Okay. So another problem or drawback with these models is that previously I had ut plus 1 was ut plus y. Suppose y is noisy. Suppose I don't actually accurately measure everything I see. There is some error. Cx, which is what is actually there, could be very small. But if there's persistent noise, this thing will just keep on growing. This is problematic. So in fact, you can include a level of output noise tolerance, lambda. So it's a fixed parameter. And I replace my update law. And this looks a bit complicated, but what it says is if I see less than lambda, I do nothing. I just keep on going. And I put that down to noise. If I see more than lambda, then I increase my control action. And so now you can prove that y satisfies, it moves into the so-called lambda strip. So it's bounded between 0 and lambda. So you achieve less, but you've tolerated more. Okay. So some of these extensions we've already started and we've made some progress on, but the ideas are sort of more of the same. And so I've tried to combine ideas from systems and control with problem in ecology, using some novel mathematics via the positivity. Yes, and these are things we'd like to do. Okay, so I presented some ideas on simple adaptive feedback control. Positivity is the crucial assumption, really, but it also implies lots of nice mathematics. Yeah, adaptive control, as I tried to mention with this airport example, hugely robust but lack optimality. You may end up using more control effort than you actually need, but without knowing your model, it's very hard to know how much you need. Okay, great, thank you very much.